Hi, Leroy. How are you?
Good morning.
How's life?
It's okay, just very tired.
Oh, yeah. 2 more weeks, 2.5.
Yeah, this semester really was a lot harder than I expected. Online classes, I expected to be easier than in person. And then,
I totally agree with you. Sometimes I'm just looking at people's work and I'm wondering why did they do that or why didn't they do that? Because when you are in class, right, I can walk around and I can point and say, look, this is not right. Online, I can only say, look at the good work and compare yours to that work, and people just don't do that. Uh, it's a matter of having not enough energy.
yeah,
It's
it's a lot more work too. Like, we have a lot more papers, a lot more writing.
yeah, yeah. But look, this is the only way. In the past, if you go to classes, you could kind of sail through without doing a lot of work outside of the classroom. And now you just can't. You have to do it. And that's what, when people say, well, I have to work, I have to support family. I understand all of that. But there is a very strong correlation between doing well and dedicating all your time to college versus spreading thin, doing classwork, going to real work, taking care of family. There's no time left for anything.
Yeah, that's something I I have to say. People who hold a full time job and go to school at the same time. I don't know how they do it.
They don't do it too well, Leroy. I have to tell you. All right. So you and I, good, which means we can play all the problem solving games. All right. So let's do it. Where is my stuff? There we go. No, we don't want that. What do we want? Oh, this. Okay. Okay, so let's see. This is what we have left. So we will do problem solving today. And then we will part for a week. The last quiz, which is quiz 12, is due on Monday, the usual. This is it. And at this point, I will start removing the two lowest grades on Blackboard from the quizzes. Thursday, December 3rd, a week from this Thursday, your last Lab 3 report is due by the beginning of the class, which is 10 a.m. And we will do just the first half of chapter 12, not the whole thing, because we don't really have time for this. And these will be the pages. I forgot to put them on the slide, but I will. So 296 until we get to 313, which is making decisions. So decisions making is going to be something that will be left behind the course. And finally, we will meet on the 8th for the conclusions. and discussions or discussion. Okay, good. So let's get going. Just you and I like that.
Yeah, I'm surprised no one is.
First of all, Tuesday is not a required class, and second, it's a Tuesday before Thanksgiving. People have other things to do. But thank you. At least you and I can talk to each other. That's going to be much easier. So stop me if you see something that is a little puzzling. Because again, as always, I tend to approach the chapter from a different perspective than the textbook just before because I think this is perhaps a better approach. Okay, so we'll talk a little bit about problems in general, terminology, kinds of algorithms and heuristics that we use for problem solving. And then we'll look at a lot of illustrations. This was a very popular topic in cognitive psychology, I would say at the end of the 20th century. It's a little less popular these days because a lot of that research has moved to sort of neuroimaging. But we are doing cognitive psychology, so this is our classical stuff. All right, just to remind you that we are in the last component of the class, that is higher level cognitive skills. We talked a little bit last week when we started concepts and knowledge, how this topic is related to what we already know, in particular perception and memory, less so to learning because we didn't really have a learning module in this class. But the idea was that now we are in the thinking realm, and thinking, according to the classical cognitive psychology, includes categorization, problem solving, reasoning, and decision making. And of all of that, we have been talking about categorization. Today we're talking about problem solving, and next week we will finish with reasoning. I also thought that I'm interested in perhaps talking to you about intelligence and expertise, and that's what Tuesday, December 1st will be. It's going to be about intelligence and expertise. It's sort of mentioned in chapter 11, but not enough, in my opinion. I think that's the most interesting part of cognition, besides language, of course. Right. All right. So, all of these lower level processes, although I don't think you would call memory a lower level process, but perception definitely depend on problem solving, right? We already discussed the idea that if you are seeing a distal stimulus, we don't know what it is, classifying it and making a decision as to what to do, approach it, run away, do something, relies on problem solving. And of course, memory. We have to know what this object is. And the general approach in the 1980s and 1990s was the traditional view that we inherited from, let's say, many of philosophers of logic, like Wittgenstein, called the normative model for judgment and reasoning. And the normative means that we expect people to rely on logic and logical inference to make the decision and to do the problem solving. That is, as if humans were thinking machines. No, if you have a computer, the computer will be very logical in its approach to whatever problem you might present to that, or artificial intelligence, or bots that we have these days. So the idea was that humans do the same. They try to be logical, they try to follow inferences, they apply sort of the extension of logical thinking into how these problems can be solved. So this normative model was predominant one until perhaps more recent work of Kahneman and Tversky, and we will talk about heuristics a little bit today, but mostly next week, that show us that humans are anything but logical reasoners. We don't do that. In fact, we really don't like thinking. It requires a lot of efforts. And we are cognitive misers. That is, we try to reserve the energy to do fun stuff, not to do difficult stuff. So, this normative model is wishful thinking. It doesn't really explain how we do all these tasks of reasoning, decision making, and problem solving. And that's where this theory came from. It was actually called an economic man, Homo economicus. That is, through logical principles, and these principles are studied at the economics departments. uh, but again, we will only start today with problem solving and perhaps move on to reasoning next week. So here is a little definition for us. The process through which you figure out how to reach your goals, starting with your current state. So this is a little bit of terminology that came from computer science, or actually in those days, more like artificial intelligence movement.
Here are some results.
Okay. So let's just think about what we do when we have to solve different problems. This is just a little taste of what one could talk about in this area. So let's say we have a broken lawnmower. Well, how do we approach this problem? We would call it a well-defined problem. Well, the easiest way is to find a repairs place and take your lawnmower to get fixed. That will cost you money, but it will solve the problem. That's okay. That's easy. Or we could try to actually fix it ourselves. Don't do it at home, as they say in commercials. Now, when you have an awkward social situation, that becomes an ill-defined problem because we don't always know how to do that. In fact, when we try to do it, sometimes it gets even worse, which means there is no real logic on how to deal with this. Now we all have this dilemma that Thanksgiving is coming and we can't have friends and family, extended family, to come to our houses because that's what they're telling us, no more than immediate people in your household. So, how do you deal with the situation of good old friends who rely on you to be in your house for Thanksgiving? And now you have to call them and say, I'm sorry, but you cannot come. In fact, I have exactly the situation. I have a good Russian friend who is very lonely. She doesn't have anybody because she lost her husband a few years ago, and she always been coming to our Thanksgiving, and this time we can't. So I could not even deal with it myself, so I asked my husband to call her, tell her that there will be no Thanksgiving gathering in our house this year. Or another well-defined problem, solve an anagram. We did that for the long-term memory chapter when I asked you to unscramble the words that had to do with parts of a flower. A well-defined problem. We know that we need to change the order of letters to get to real words. Okay, so 2, 1, and 3 are well-defined problems, and number 2 is an ill-defined problem. That's sort of the easy classification of problems. We don't think of them this way, of course, but that's how we approach them. All right, so if we take the cognitive psychology approach, which is information processing, how do people try to solve a problem for which a solution is not obvious, although the problem may be well defined? So we'll talk about these two classes of approaches. One is called searching. Search, if you have a bunch of potential solutions, you're going to select one of them. Versus restructuring, where you have to do something with the problem itself before you can try to solve it. And that, again, is something that will allow us to achieve the goal of problem solving. So the first one is represented well by the mean-end analysis of problem solving that originally came from cybernetics of computer sciences in the 1970s. And here are the two pioneers, Newell and Simon. And this is their terminology, which is widely adopted by cognitive psychologists. So we have a problem and it has components, right? So there's something called the given, that is the initial state of the problem. Then there is a goal, or maybe goals. That's what we need to achieve at the end of problem solving. Then there are certain things we can do called transformations. How do you transform the given to reach the goal? And in the process, there may be things that make it difficult for you to do so, called obstacles. So that's sort of the general elements of the problems that are well illustrated in a number of problems that are presented to you in the textbook. And of course, one potential way of doing that, proposed by Newell and Simon, was to use means end analysis. I mean, it's a technical term, and we'll go through this in a second. Basically, it says we'll start with a given state represented somehow, then take the goal state also represented somehow, then compare the two and see if you, well, see the differences you will notice between the two. And your job will be then to reduce the difference one step at a time, which means you'll have to reduce differences as you go several times. That means you will repeat the means and analysis in solving the problem. Now, the reason why they decided to do it this way, because, like I said, they were computer scientists. So they were actually programming a computer to solve problems. And a computer has to be given specific steps. It's not particularly creative yet, especially in 1972. All right. Again, this is their terminology. There's also something called intermediate states. That is when you reduce the difference once, you're going to get an intermediate state, something between the goal, the given, between the given and the goal, right? The initial state and the final state. And those difference reductions are known as operators in their system. An operator is an action that you have to do that will change your current intermediate state to the next intermediate state, or if it is the last one, the goal. And then obstacles will be constraints on the way that you have to work around. Again, remember this was designed for a computer, but then it was adapted by cognitive psychologists to explain how people solve well-defined problems. So one could think of that as a graphical representation of a tree, like with branches. So you can go one way or you can go another way, and this whole thing would be called the problem space. So in this problem space, your job is to find the path that will lead you to the goal state in the least amount of steps, or the least effort path, so to speak. Right? Again, for a computer, it doesn't really matter. A computer, especially now, can have billions of operations in a second. But for a human whose resources are limited, it's important that you select the path that will deliver the results in the most efficient way. So it's just a terminology that you will see in various descriptions of problem solving. So we know how to call that. It's called an algorithm. So an algorithm Again, think of a computer program, a script that you would write. Do you know any programming languages, Leroy? Can you write a script?
A little of HTML.
Hmm. But nothing serious like Python or Shine or R. Right?
No.
That's actually a good set of skills for real life. But in all these approaches, whatever that is, in the old days it was C++, before C++ it was PL1, Fortran, all of these computer languages, they all are based around the algorithms. So there are systematic rules, and you have to apply them in a certain order, sometimes multiple applications. But the good thing is that when you apply an algorithm, the solution is guaranteed. That is, you can't fail. So one could think of the way they taught us in school how to multiply double-digit numbers. Again, if you apply the algorithm, all the steps that you have to do to get to what 38 by 17 will be, you are guaranteed the correct result. Okay? So when the problem is obviously soluble, that is, you can see the goal, then algorithm could be the best thing that can happen to you if you know the algorithm. All right. So a lot of teaching that has to do with professional skills is about sort of algorithmic learning. You learn the steps of your trade, even in highly creative and ill-defined areas like science. There are tons and tons of algorithms that can make students' life much easier. So it's logical, systematic rules. It will lead, the algorithm, it will lead to solving a problem by reaching the correct answer. And the best thing is if you have a sort of a recipe, right? Just follow the steps. You will be able to solve the problem, right? So if you think about fixing that lawnmower, well, you need to find online the place that fixes mowers. You have to find out if they're open. You have to have a car or ask them to come and get it, have enough money. All of these are very simple things to follow, making it into an algorithm solution for this particular problem. Okay. Now, as opposed to something that is called heuristic. Now, heuristic, or heuristics, plural, would be a rule of thumb that we quickly apply to solving a problem without necessarily getting the right result. That is, algorithm, remember, will always deliver the correct answer. It will solve the problem for you. Heuristic, most of the cases, will also deliver the correct solution, but there will be cases when you will make an error. So the trade-off between an algorithm and heuristic is efficiency, time. So if you apply a particular heuristic in 90 whatever plus 95% of the cases, it will be as good as applying an algorithm, but there will be 5% of the cases when you will be wrong. So you kind of think about it. Should I spend a lot of cognitive efforts in solving the problem using an algorithm, or should I just rely on one of these quick and dirty tricks, which would be the difference between algorithm and heuristic? We'll talk more about heuristics next week. So they come from the work of these two people, Kahneman and Tversky. David Kahneman is still with us, thank God. He is also a Nobel Prize winner in economics, and his colleague Amos Tversky, who died long ago. So they were the ones who came up with this idea of using heuristics, sometimes called judgment heuristics, in human reasoning. In this case, people specifically choose a heuristic over an algorithm. And it's also one of the best way of solving a problem or judging something when you are not certain about the results, like a difficult social situation. But even when the results are certain, if you make a mistake, you may perhaps learn from it and apply a heuristic a different way next time. So this is just a small subset, not the whole thing. If you're interested, then there is a wonderful book by David Kahneman called Thinking Fast and Slow. This is a small subset of heuristics that they have proposed in the human experimentation, which means that they actually conducted experiments with people. So there is something called representativeness, availability, simulation, anchoring, and adjustment. Like I say, these are the four main ones, but there are more and more. Again, in today's class, we won't look at this because that's the topic of judgment and reasoning and decision making, chapter 12. So let's look at an application of algorithm versus heuristics and problem solving, and we'll start by means end analysis, and then we'll get to hill climbing. The distinction between the two is a little blurred, I would say. So don't get too hung up on the terms, as long as you understand how it works. Again, just to remind you that these are the four components that this approach requires you to implicitly use: a given state, a goal state, and transformations that are implemented by operations, and obstacles on the way from reducing the difference between the initial state and the goal state. This is how it would go. Let's see if we can apply it. So first, you're going to create a representation of the current state. Well, sometimes this current state, the initial state, is given to you. On most cases it is. Sometimes you have to restructure it. Then you have to make a mental representation of the goal. Again, we know what it means to solve a problem, so it's not a particularly difficult part. Well, the next step is more interesting. Now you have to calculate the difference between the current state and the goal state. Again, this all sounds very abstract until we get to an example next. We're going to take our first step in reducing the difference. That's means end analysis between the current initial state and the goal state, or later on between the intermediate state and the goal state. And we will continue to apply step 4 until the difference is reduced to 0. That is, we got from the initial state to the goal state. The job is to do it in fewer steps as possible. Okay, so here is our famous example of means end approach to problem solving called the Tower of Hanoi. Okay, let's see, Leroy, if you can do that. I'm gonna show you something. All right, can you see? I have the 3 pegs. They're marked A, B, and C. And I have 3 disks here, right? So this is my initial state. My goal state, or your goal state, is to have these 3 disks be moved to peg C. All right, so that's the goal state. And there are 2 restrictions, 2 obstacles. One is you can never have a situation when a larger disk is on top of the smaller disk. So that's not allowed. And then you can never move 2 disks simultaneously. So this is not allowed as an operator. So your job, Leroy, is to figure out how to solve this problem, Tower of Hanoi, in as few steps as possible by abiding to these 2 restrictions. So think about it for a second and tell me what your first step will be, the first operation, operator.
Move the red one from A to C.
1. Mm-hmm.
Move the green one from A to B.
2.
Move the red one from C to B.
3.
Move the blue one from A to C.
4.
Move the red from B to A.
5.
Green from B to C.
6.
And red from A to C.
Fantastic. You did it exactly right. Did you notice there was one particular step where instead of reducing the difference, you actually introduced more? So when you were in this situation, when you were here, now was it here? No, what was it? So this is forward, we are reducing the difference. This is forward, we are reducing the difference. Okay. Okay, here. This is the step when you have to take the red one and put it back on A. So that is sort of going back to the way the problem was represented in the beginning. And people really hate that. This sort of reverse step that takes us back. But it's inevitable because if you don't do that, you won't be able to solve the problem. All right, Leroy, let's challenge you again. Now we have 4. Okay, go ahead. So orange, red, green, blue.
Move the orange from A to C. I have no idea.
Well, okay, let's try it. We only have, with the red one, we don't have a choice, right? We can only move it to B, right?
Yeah.
Okay. What do you suggest we should do next? We have 2 paths here, right? We can take the orange one and put it here to B.
Yeah, and move the orange from C to B.
Okay, yep.
Move the green from A to C.
Yep.
Move the, I did it wrong. Move the red and orange from B to C. No, or you can only move, yeah. Move the red from B to C.
Yep.
Move the orange from A to C.
Yep.
See, I started it wrong.
No. Okay, let's, we only have one choice here, right? For the blue one. Where will it go?
E.
B, yep. Okay, let's try. What would be the next step? Again, we can use only this one and we have 2 choices. B or A, which one would you prefer?
E. The orange to B.
Yep, okay. Again, we only have this one step, right? Okay, what would be the next one? All right, there's only one step, right, Leroy? We can only use, because we can't take the green one. We're gonna take the orange and move it back to A, right?
In my mind and trying to figure out the next few steps.
Ah, okay. Well, from this point, what would be the next step?
C to B.
Okay. All right. So again, we have orange. We have two possibilities, B or C.
I guess B. And A to C.
No, I think you've made a mistake already. Okay, so this is 4 disks, right? But it certainly is doable the same way it is doable with 3. It just takes a few more steps, but it's a well-defined problem. We know where we start, we know where we want to finish. And the problem is that we have these intermediate operators that we don't want to do because they seem to be taking us back, right? So here we are with the disks stacked in the middle when we want them to be stacked on C. But we have to go through this. So this comes from this very interesting legend of the Tower of Hanoi problem that was created by Lucas in 1883. So here is how it goes. In Hanoi, there is a temple in which there is a tower of 64 sacred golden discs. Now, this is just 4. But imagine a stack of 64 trimmed with diamonds. The discs are stacked on top of each other, with the largest at the bottom and the smallest on the top. The monks must move the discs from one location to another, one at a time, such that the larger disc is never placed on top of a smaller disc. So it's just like this little representation. Besides the original location and the new location, there is only one other place in the temple sacred enough to hold the discs, right? So that gives us the metaphor of 3 pegs. The legend holds that before the monks complete the task, the temple will crumble into dust and the world will end. So you and I played with 3 discs and 4 discs. What do you think will happen in terms of time and efforts if you have to move 64 of them?
A lot more time and more effort.
Okay, how much more time, Leroy? What do you think? When will the world come to an end based on the 64 discs?
I have no idea.
Okay, guess. A wild guess. Let's assume, just for the sake of argument, that it takes 1 second. Of course, that's not realistic. 1 second to move one disk to one of the 2 locations, the intermediate one or the final one. So monks are like little robots, 1 second per operator. How many years will it take them to perform the task with 64 disks?
It depends on how many steps can be done.
Uh-huh. So what's your wild guess?
Probably that it can't be done.
All right. Okay, let's look. This is the representation in case if I don't have a prop, which I actually do. This is how we would go about it, right? So we have the current state now. The current state is -1 disk with 1 disk already where it should be. We calculate the difference. We still need to move these 2, but we can't put them directly on the 3rd peg. we have to reduce the difference, and we do that by moving the next disk to the middle peg, right? So this is in case we don't have an actual toy. And this is what it will take. So to move 64 disks in the matter specified will require whatever this number is, 18, blah, 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 blah. So million, billion, trillion, quadrillion, quintillion, 18 million quintillion, 18 quintillion moves. And like I said, at the rate of 1 move per second, this would take the monks approximately 5 billion years. So we are safe. The world is not going to come to an end based on the Tower of Hanoi in the near future. Again, it's a well-defined problem. A computer solves it with 64 disks in no time, but because it can be solved by an algorithm. And if you're human, going through an algorithm is going to take you 5 billion years. Okay, here is another one, which you should recognize now. So based on hobbits and orcs, okay? Also known as missionaries and cannibals, also known as sisters and brothers, and so on. There are many versions of this problem. So this is how it goes. On one side of a river, there are 3 hobbits and 3 orcs. Orcs eat hobbits when they outnumber them. The creatures have a boat on their side that is capable of carrying 2 creatures at a time across the river. The goal is to transport all 6 creatures to the side of the river. At no point on either side of the river can orcs outnumber hobbits, or they will eat them. So what is our initial representation? So this is our river, okay? And these are the 3 hobbits. And these are the 3 orcs. So our goal should be having all 3 hobbits, right? And all 3 orcs on the other side. And this is our boat. So Leroy, what should be your first step?
You have to transport them one at a time, right?
Well, if you take them one at a time, who's going to return the boat back? The boat has to be manned, or well, they're not people, but it has to be manned by 1 creature. So, and it has space for 2. So who are you going to take on the first trip?
1 hobbit, 1 orc.
Perfect. Let's do that. I'm going to take 1 hobbit, 1 orc, right? And take them across the river. Excellent. Who's going to return the boat? The hobbit or the orc?
The hobbit.
All right. So the orc stays here, orc number 1. And hobbit comes back. So now we have 3 hobbits and 2 orcs. Okay.
Take
So what's the next step?
2 hobbits. So 2 hobbits.
Okay, you're going to take 2 hobbits. So let's get rid of this. So now we have 1 hobbit and 1 orc. Now we're going to take 2 hobbits. Are you sure? See what's going to happen now, Leroy. Oh, we already have 1 on the side, so all these guys are gone. And there's this one is on the other side. So there's only 2 orcs left, right? All right, so we're going to go. Are we going to leave 1 hobbit, right?
Leave 1.
Okay, and the other one is coming back. All right, so he's coming back, and there is 1 orbit is here, and 2 hobbits are here. All right, so he's going to take, so all these guys
Well,
are
we
gone.
can't do that 'cause now there are numbering them.
Yeah, okay, so we're going to take, so now we will have 2 orcs here, and then in the last exchange for, well, the same hobbit who's been going back and forth will bring the last orbit. Perfect. And this is just like this problem, right? Like the Tower of Hanoi. It's through means end analysis by reducing the differences, keeping in mind the restrictions which require us to go back to the intermediate state. And that's, again, this is what people don't like. So sometimes these problems create issues for participants when they are asked to solve this. Goody. Let's get rid of that. Now, Newell and Simon programmed the Tower of Hanoi into the artificial intelligence agent, who they call general problem solver. That's the term that they used. And this is how this GPS solved the Tower of Hanoi, precisely by following the algorithm. Here is the goal, here is a sub-goal, and then going through the operators and confirming the restrictions. And it works. Again, algorithm will work if you're willing to, and there is no other way to solve this. There is no other way to sort of heuristically approach this problem. It has to be solved through an algorithm. But again, we are lining up the sort of the computer with a human, thinking that human will behave just like the computer. It will go through the steps. And in this particular problem, the Tower of Hanoi, or Hobbit and Orc, Hobbits and Orcs problem. Again, algorithm is the best solution. Good. Now let's try something different, Leroy. See if you can solve this problem. So water lilies double in area every 24 hours. On the first day of summer, there is only one water lily on a lake. It takes 60 days for the lake to become covered with water lilies. On one day is the lake half covered with the lilies.
If it takes 60 days, it's one day before
Which would be day number?
59.
Absolutely. But you see, here's the issue, right? If we were to start doing it via brutal force by saying, okay, well, here is our initial state, one lily. Here is our, this is day 1. Here's our final state, 60 days. One could start doing it by saying, okay, well, we need to get from day 1 to day 60, so let's go to day 2. Day 2 will give us 2 lilies. Day 3 will give us 4 lilies, right? Day 4 is going to give us 8. So technically, especially if you have a computer, you could solve the problem this way. However, as humans, we don't do that. So here one would say, okay, instead of going through this means end reduction from left to right, so to speak, let's do it backwards. Let's start with the goal, which is the entire lake covered with lilies. And instead just doing one step, going back to 59, and which is exactly what you did. Perfect. Brute force by reducing the differences between days going forward is not going to work. It will work only for a computer, but not for a human being. So sometimes you need
I
to.
think if you actually gave a number of what it would be on the 60 days, it would be more confusing and more people would try to do it mathematically and pay less attention to the wording.
Yes, you're absolutely right. That's the whole point. So sometimes instead of solving the problem sort of algorithmically, you have to creatively think about the goal state and see if you can achieve it through other means. And that's very hard, especially if you have just been prompted to do it the way we just did it with the Tower of Hanoi, by step using an algorithm. Excellent. It's such a joy working with you. Okay, so that would be brute force versus going backwards and noticing that. And that is the biggest problem in problem solving of that type. Okay, good job. So what are the steps looking at this approach from the early research in cognitive psychology? You have to create an initial representation. In this case, for all three problems, I gave you the initial representation. So it's either, oops, that is not going to be the one. It's either this, right? Don't run away from me. Or it's our orcs and hobbits on one side, or it's an empty pond with one lily on the first day. But many problems require you to actually come up with your own mental representation, or maybe physical representation, if it's something that you can actually do with your hands. Okay? Then you would start generating and evaluating potential solutions, and that's the hardest part, right? If it's a large problem space, how are you going to, so you can generate this potentially infinite problem space, but how do you evaluate each potential path, right? And then you actually have to execute this whole thing. So the reason why this sort of presented here in those terms is because it is the quintessential computer science problem, and that's how they deal with that. I already mentioned this very useful distinction for a well-defined problem. We have all the components. We have the initial state, we have the goal state, we know what the operators are and what the restrictions are. But in ill-defined problems, we don't really know about the operators or operations, and there will be a large number of solutions possible. But again, not in these classical problems, but more of a problems that have to do with everyday life, like that social, awkward social situation. So let's look at yet another one. Sorry to make you work, Leroy, but at least we'll do something useful. So let's start with how you would approach this problem by doing the first step. What would be the initial representation or the initial state? So the price of a notebook is 4 times that of a pencil. The pencil costs 30 cents less than the notebook. What is the price of each? So here, forgive me for interrupting your thinking for a second. When these kinds of experiments are done with actual participants in the lab, they are asked to talk through how they will be solving the problem. It's called a verbal protocol. So have a look at the example again and see if you can verbalize what is going on in your head.
that I think the only way it can be less and still cost 4 times more is if it's a negative number.
Mm. But remember that the step that you need to do, Leroy, is to come up with an initial representation. So imagine that you have these objects, right? Because that's easy. A notebook and pencils. We know the price of one pencil is 30 cents less than the notebook. So let's think if you had access, well, I don't have that many pencils, but I have plenty of pens. So these are my pens, right? Of my pencils, think of them. And here is my notebook. Oops. Something, okay? So how would you represent this problem in such a way that it will allow you to sort of solve it quickly? Pencils and the notebook. Let's say you want to equate the price of the notebook to the price of a number of pencils.
So I guess choose the value.
All right, so let's do it this way. I'm gonna have one notebook and one pencil. Are they equal in price?
No,
Which is more expensive, the notebook or the pencil?
the notebook.
Okay, great. Let me add another pencil. Oh, so now I have a notebook and two pencils. Are they equal in price?
No,
Okay, I'm gonna add a third one. Now I have three pencils and one notebook. Oops. Are
no,
they equal in price?
no.
Okay. Now I have four. Are they
Yeah,
equal? Okay. So now you can solve the problem, right? One notebook is equal to how many pencils?
4.
Four. And one pencil costs 30 cents less than the notebook. So what's the price of the notebook? What's the price of one pencil?
40 cents and 10 cents.
Fantastic. Yes. Exactly how you would solve it, but you have to sort of think of it first in terms of how you would represent that. If you were trying to sort of, I mean, you could also, of course, write an algebraic expression, right? But if you physically represent your initial state like this, which is the picture on my left, versus, and then you can now solve the problem easily. So this initial representation for a problem that's not given to you as well defined sometimes gives you the solution right away. Okay, and that would be the arithmetic if you wanted to do that using algebra. But we don't need to even use algebra if we think of that in terms of actual graphic representation. That's why, I don't know if you're familiar with some of these learning systems that have been proposed to help people learn, like mind maps or concept maps. Have you heard about those?
No.
Oh, interesting. Let's see if I have this book close by. Give me 1 second. Uh, I can show you a concept map. That's easy. So, what would be a concept map? So, for example, this is a concept map of the model of memory that we discussed a few chapters back. So the concept map allows you to graphically represent various components, right? and they are structured. So here is the model itself, and these are its components, and this is the sensory memory that we talked about. Okay, so one could have a whole chapter, well, not a whole topic represented like this. Here is another one. Remember the experimental evidence for short-term memory versus long-term memory. And that has to be with a bunch of experiments like a serial position effect, right? So here we have the serial position effect, and we have recency and primacy. And it gives us evidence for short-term memory and long-term memory. So these are the concept maps. They some people swear by them because they really work if you are looking at something very complex. Here is another one. This is the working memory model by Alan Baddeley. We have the central executive right here, and we have, this is the whole system. This is the phonological loop. And these lines give us the evidence for this phonological loop. So what are the effects that you can demonstrate that will tell us that we do code information verbally? So we can have articulatory suppression, word superiority effect, and so on. Phonological similarity. So these methods are very helpful when you're looking at the complex topic, because it allows you to represent it in a very succinct form, giving you sort of a bird's view of the topic. And I can show you later the mind maps. So this is the concept maps. Concepts are mapped out, and the way they are connected is represented by lines. Right. So once we have this initial representation, in this case, the initial representation of this notebook and pencil problem, now we need to generate potential solutions. And what often happens in the situation that we generate them in sort of in the same way, which can be a problem by itself, because it can take us into the sort of dead end. So let's have a look at an example of that. Let's see if you can solve this problem, or you can think about it, how you would solve it. So imagine in your mind's eye a square sheet of paper. Mine is not particularly square, but doesn't matter. Now fold it in half in your mind. Okay, now fold it in half again and again and again. And continue until you have folded the paper in half 50 times. So the initial representation of this problem is easy, right? It's just a square sheet of paper. Then the next step is the generation of possible solutions and selecting the one that will lead to the goal state. But doing it now using the sort of graphic representation that helped us with the notebook and the pencil problem is not going to work here. Right?
Yeah.
Because after 5 or 6 folds, you sort of run out of paper. So here, the solution would be much better if you were to use, this is a different problem that I haven't shown you, if you use the actual mathematics, because the visual solution here is not possible. So a better way would be to say, let's use math operations. Okay. So the second fold would be 4 times.
It would be, yeah.
It's going to be this number. The thousand millions, billions, trillions. So that would be a one-step solution. Whatever this number is, you would just say it's 2 in 50 power, versus trying to solve it visually, which worked beautifully for the notebook and the pen. So at every step of the way, we may be running into problems in our problem solving. Now, but this was well-defined problems. What about an ill-defined problem? An ill-defined problem doesn't give us a good initial state. We kind of know what the goal state is. So perhaps the way to deal with them would be to establish sub-goals, that is the intermediate states. Or perhaps we should restructure the problem. So it becomes, if not well-defined, but less ill-defined, sometimes also called poorly defined problem. Okay? So it's the shift in the representation of the problem and its operators. And the shift is really, really difficult. That's why there is this big component of problem solving idea that it has to be done via insight. Have you ever experienced an insight, Leroy, in your life?
No, I probably have. I just can't think of the situation right now. But what does come to mind, the day of my accident, a little while before, like my mom had this feeling that something was gonna happen or happen. Like she had like, I don't know how to explain it. It felt like an electric current run through her body a few minutes before she was called and told about the accident.
Hmm. Yeah, but it's not what you're talking about is some kind of a premonition. Well, I'm interested in asking you if you can think of an example from your life where you were stuck with a difficult problem, whatever that is, and you could not solve it, and you could not solve it, and you thought about it for a while, and then suddenly you got an insight. Suddenly the solution appeared apparently from nowhere.
Like an aha moment.
That's right, like an aha moment.
I had one with the Tower of Hanoi.
Hanoi. Ah, okay. When was that, and how did it sort of come to your mind? Can you verbalize that?
The first one with only three. I was kind of doing it in my mind before I started. And like a few seconds later, I was like, aha.
Interesting. All right. So this is aha moment is technically called an insight. And there is actually a German word for that, Einstellung. So the book and all the classical texts on problem solving talk about the scandal problem. Now, it's always fun to have it sort of done physically in class, which we don't have an opportunity to do so. So here is the problem. If you remember about it from the textbook, then we won't I won't ask you to solve it. But if you don't remember, see if you can come up with a solution. So you have a candle, right? A relatively thick one, not the one that goes onto a cake, not the thin one. And you have three in addition to a candle, you have two more objects. You have a box of matches and you have thumbtacks. How would you mount a candle on the wall and light it using these three objects?
I guess somehow use the thumbtack to hold the candle.
Mm. Okay, well, I don't actually have a candle with me, but let's imagine that this is a candle. See, it's kind of thick, and your thumbtack is short. So if you were to put that in the wall and try to set the candle on it, and it's not going to work because it's just too thick.
You can use the matches to mount the candle.
Mm-hmm.
So it's like part of the thumbtack.
Well, it's going to be the same problem. All I'm saying is that your thumb tack is not long enough to support the candle. Even if you have two of them, let's say you have two, and now you're going to put the matches to like create a little bridge, also is not going to work because this candle is too thick to sit on them. That's going to be a problem. All right, I'm not going to torture you because it's a classical one, right? So here is the idea. If you take the matches out of the matchbox, use it as a little shelf instead of using it as a container. So now you can use the tack to attach the empty box to the wall and put your thick candle on top of that and then light it.
See, I was thinking like a matchbook.
Mm. Well, I think it said match a box.
Yeah, but for some reason in my head,
Okay.
a book.
But in the laboratory, and again, this is a classical work from 1970s, even before, the problem is that people think of a matchbox as a container that contains matches. And of course, you need matches if you want to light your candle. So they're being sort of led down the garden path by thinking that they will have to use matches and matchbox for this function only, as opposed to thinking creatively and using the matchbox as a little shelf. And this is known as functional fixedness. So we often get stuck in solving a problem of this type because we think of the objects, operators, right, in the traditional way, giving us a lot of fun in research on creativity. So how creative can it be if somebody gives you a particular object and asks you to come up with multiple uses that are not traditional? So let's see if you can do it, Leroy. Uh, Oh, imagine a wire hanger, the one that you get at the dry cleaners, right? Just a plain metal thing. All right. I'm going to give you 30 seconds to think and then try to name as many creative new ways of using that wire hanger as you can without using it as a hanger. You see what I mean? All right. So I'll give you 30 seconds to think. Are you ready, Leroy? So your job is to just name these new uses and I will count and see how many of these new uses you can come up within a minute. So I need another, hold on a second, I need another timer for that. Oops, that is not, where is my, there it is. Clock, stopwatch timer. Let's, are you ready? Go.
An antenna to like pick a door lock on a car.
Okay.
You can do so many things expendable.
Just name them, name them.
You can use it as a skewer,
Okay, 4.
as a wire, because the metal and the conductive.
Okay, 5. Okay, your timer is up. So you came up with 4, well, maybe 4.5 potential functions. So in this is a very traditional approach to uh, creativity, like a little lab type of test. So that number, which usually average people come up with, is about 6. So anybody who can come up with more than 6 in a minute supposedly is more creative than anybody who comes up with 6 or fewer. So you're an average person, Leroy. Amar, can you, are you with us? Are you,
And I'd rather be average than subordinate.
absolutely, yes. And most people actually are average, so that's nothing new about it. Amar, are you with us? Or are you just hanging out there in the background? Okay, so still just the two of us, Leroy. That's good. All right, so this was functional fixedness. It's when you tend to think of the objects the way they're normally used, and sometimes it becomes an obstacle in solving the problem because your prior experience sort of directs you into thinking of a box of matches as a container as opposed to thinking it of something that could be used in a different way, giving us a solution. In fact, if you go to like an MBA program, there will be a course where they spend a lot of time teaching you to think creatively, to solve sort of business problems. Apparently, a lot of business problems are ill defined ones, and functional fixedness could be a big obstacle in developing this way of solving problems creatively. Um, But so think of the functional fixedness as a perceptual problem also, because we're looking at this box and we think of that as a container. What will happen, interestingly, right? So about 10% of people in the original study of Dunker in 1945 solved it, the mounting the candle on the wall. Interestingly enough, that if you take the matches out of the box and have them in a separate little bag and have a box empty, increases people's, or in a box in which you don't have matches but have thumbtacks, increases people's solution of this problem. When you now give them the empty container, they don't have to think of it as a container. They can use other interesting ways. Now, and at YouTube, you can actually find a bunch of old Gestalt clips of this kind of work of insight problem solving with primates, with chimpanzees in particular. So one of the well-known examples of that is when there was a banana that was hung on the ceiling of the cage, and the chimp could see the banana but couldn't get it because it was way too high. But what they did, and that was Kohler's work, Wolfgang Kohler, there was a bunch of boxes sort of scattered around in the cage. So what was interesting, the monkey actually thought for a second, or it looks like it thought for a second. And then it started collecting these boxes and sort of putting them one on top of the other, and then climbed on that little tower and got the banana quite easily. Another famous example is um, this work has been done in Germany in particular, where there was a plastic tube long enough attached to the cage so the monkey could see the tube and could reach it. And what they did, they put one almond into the tube. Of course, the tube is long, the almond is at the bottom, and the monkey wants to get it. Well, how do you do it if you're a monkey? You need an inside solution to this. And what monkey came up with, the chimp actually, was to
A,
go back
vid-
to. Hmm?
a video within the first thought ebook. I actually posted on one on my not on my blog.
Aha, excellent, yay, good, 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 good. So there's a bunch of those interesting clips on how monkeys and chimps come up, and we don't really always think of them as that creative, but there are some experiments that actually compared chimps and children on problem solving. That would be an interesting blog entry for somebody. Okay, so all these variations to the candle problem make it easy to solve. So if you present the box as empty and the text separately, or if you present the text in the box but they're not matches, they're tags, all of that increases people's um, success with this problem, which was replicated in 1968 by Glucksberg and his colleagues. Right? So, like I said, this little test of creativity by naming unusual or not expected potential uses of an object are an interesting way to think about creativity and problem solving. Not, of course, just the objects, but in general in life. So this is the German word called Einstellung, which is sort of new attitude. You're thinking of the objects in a new way, and that gives you the way to go around this rigidity in problem solving that is known as functional fixedness. So you're fixed on this one particular function of the object. Let's try another one. Okay, you may need a notebook. Leroy, do you have something to use? Okay, good. So here is the setup for the problem. So we have these three containers, jugs, the blue one, the red one, and the yellow one. And they can hold different amount of water. I'm not giving you any numbers yet because they will come on the next slide. So the volumes, there's always the case that the yellow one is smaller than the red and the red one is smaller than the blue, but the actual amount of water will differ. So I'm going to show you 6 cases, okay, that will specify the amount, the volume that these jugs can hold. And then there will be a problem. That is, you will need to obtain a certain amount of water, I think it's in liters, by using these jugs. And you're going to get the water from the well and then pour it into another vessel. So you have to do it 6 times. Let's see if you can find the solution. All right, so in problem number 1, the goal is to obtain 100 gallons in this cylinder. And what you know, this is your initial state, is the largest jar, the blue one, holds 127 gallons. The next one, jar A, holds 21 gallons, and the smallest one holds C. So how are you going to use these 3 jugs to obtain 100 gallons of water? So try to write a solution in your notebook for this problem number 1.
Easiest way is to fill up jar B.
Okay, so we're gonna take, oops, come back. Let me stop this. So we're gonna take B, right?
Yeah.
Okay, that's 127.
Use jar A to remove 21 from jar B
All right. Mm-hmm.
and use 2 jar C. So twice with jar C.
Perfect. Right, and that will give us
One
100 gallons. Perfect. That's what we want. Okay, let's do the next one.
fill up jar C 3 times and empty into jar A.
Okay. So you're gonna take jar C 3 times?
If you take jar A,
Okay,
fill
18.
it 3 times with jar C, you'll have 15 gallons.
Yeah, but remember we are pouring everything into the cylinder. We're not using the jars themselves.
Uh,
So you can take jar C 3
3
times, right?
times.
Mm-hmm. Okay. What about number 3?
Do jar one twice with jar A. I'm sorry. Once with jar A and twice with jar C.
Uh-huh. And what do you think about the first one? Do you think we could do B minus A minus 2C?
Oh no. Not if you're feeling.
Uh-huh. Okay, Leroy, try number 4. Elmer, try number 4, 5, and 6, and tell me how you would use the jars to obtain the 31, 20, and 25. So could we, for number 4, could we take 59,
And
subtract
remove A
20, right?
and remove C twice.
So we could do 50 minus 20 minus 4 times 2, right? And that should give us
31.
31. Yeah, and it does, right? How about number 5? Will that give us
A minus jar C.
A minus jar C? Yeah. Okay, but it would also work if we were to go the same way. 49 minus 23 minus 3 times 2, right? So you see what I'm trying to show you, that when people start solving this problem, when they solve the first one by creating this B minus A minus 2C, they are happily continue to use the same solution for all the problems. But as you can see, like you just showed us, that A, if you take pour 3 into jar C, you're going to get 20 without going through the solution. But people get so fixated on the solution that they have found, B minus A minus 2C, that they solve this problem, especially the last one, right? The last one is also very easy. You're just going to take jar
A
A, right,
C.
minus C, and you're going to get your 25. So, and the same happens a lot in sort of exams and tests, where people just doing this without looking at much simpler and faster solution. Yes. And that's a very classical test that is given to participants, was given to participants in the 1970s. All right, so you would go through this algorithm. It seems to work well. Okay, so there is the first case of 127, 21, and 3, and you just go through this and it works until, of course, you get to the fact that you can just do A minus C, and that would be the solution, right? Right. And then number 5 and number 6 can be solved the simpler way. But again, in the real experiments, very few people find this. They continue to go with this algorithmic approach that worked. So these are the certain assumptions. If you handle your problem this way, you will sort of remember that, and you will continue to use this approach when you are presented with another problem, but you can rely on your memory to sort of retrieve the solution that's there instead of trying to think of a new one. That's, again, goes to the idea that we are cognitive misers and we don't like to look for new solutions if we can rely on something that we already know, even though it may not be the most efficient one. All right. Do you want to try this one? Let's say we have 6 matches. We cannot break them. I'm asking you to try to use these 6 matches. I don't have any matches, but I have pens. If you were to use the 6 matches and create 4 equilateral triangles. Equilateral means, right, that the sides are the same, right? So that would be something like this.
Make a square and split in half both the long way and the other way.
All right, well, draw it in your notebook, Leroy, and show me.
I have a hard time writing.
Oh, sorry. Okay. Amr, do you have a solution to this problem? Now remember, you cannot break those matches, and your 4 triangles have to be equilateral. It means that each of the 3 sides are the same. Well, you can imagine one possibility, so I certainly can draw that. And this is what people come up with immediately. So a lot of people suggest that as a solution. Can you guys criticize that? why this is not the solution for this problem.
Because the middle ones need to be longer.
Mm-hmm. Well, the problem here, so we need 4 triangles. All right, do we have 4 triangles here? Actually, I have more than that, but we certainly have 4, right? 1, 2, 3, and 4. The problem here is that these triangles are not equilateral. That is, the side that is here is longer than these 2 sides. So that is not a solution. And the solution is to get away from the 2D representation of this problem. So instead of putting matches like this, right, flat on your table, you're going to try to lift them, making a 3-dimensional object that will look like this. All right. So now we have our 6 matches. They are not flat 2-dimensional, they are 3-dimensional, and all 4 triangles are equilateral. The problem is not seeing that unless you play for a while, and it's usually a couple of people who would come up with this solution after trying it for a while. But everybody loves this, thinking, wow, it's so easy. But it's not. So again, you need to get away from this functional fixedness of, if you have something that you can put on the table, put that on the table, and think, instead of 2-dimensional representation, think of a 3-dimensional one. Try this one. So Leroy, do it in your mind's eye because it's hard for you to draw. So now you need to have 4 straight lines that connect all 9 dots, and you cannot lift your pencil from the page. That is, you have to keep doing it until you have finished with 4 straight lines. All right, so here is, aha, you know this one. Okay, good. Okay, Leroy, so these are the 9 dots. What if I try to connect them? 1, I'll show you in a second. 2, 3, 4. If I do it like this, I have 1 dot that I did not connect. If I go through diagonal, I will still have the same problem. I will have 1 dot that's not connected. So the solution here is, after you think for a while as a participant, is to take this 3x3 representation and imagine that it's 4x4. So you have 4 dots horizontally and 4 dots vertically. So I'm going to do that to show you what I mean. Does it help, Leroy? Can you think of a solution? So now I have a 4x4. So remember, all I need to do is to connect 9 dots. So I could do, without lifting my pencil, right? I'm not representing it well, but if you go through a 4x4 as opposed to 3x3, you will be able to solve this problem. Again, we are so fixed on seeing the night dots that 4x4 does not come to us as a solution. Okay? This is all about functional fixedness that has been studied to death because it's such a good example of how we fix on something and don't see the other potential solutions. But what helps sometimes is this insight. And insight usually comes after you look at the problem, try to solve it for a while, but don't kill yourself and walk away. Walk away, do something, come back. Like if you have a dog, you can walk a dog, or you can take a shower, you can have lunch, and then come back. So let's see if you guys, the two of you, can solve this problem. We don't have time for you to walk away. So now we have these 4 chains, A, B, C, and D, right? Each has 3 links, right? So when you open the link, that costs 2 cents. And when you close the link, I don't know how to represent that. That costs 3 cents. And at this initial state, all the links are closed. So now you have to create a necklace that has all 12 links together, but you're cheap. You don't want to spend more than 15 cents. So if you start with chain A and open one link, that's going to cost you 2 cents, right? Then when you connect it with B, right, you have to close it. That's going to cost you 3, right? Continue doing that. You have to open and close, open and close. Can you have a solution to this problem?
No, it's 2 cents to open, 2 cents to close, right?
So 2 cents to open, 3 cents to close.
Oh,
So that's the problem. So if you sort of go through this algorithm of opening and closing, opening and closing, opening and closing, you will spend 18 cents. But you want to make sure that your necklace is only 15 cents. So you need to do something about some of these steps that would allow you to shave off these 3 cents. And the solution to this, oops, no. Let's clear it first. The solution is to use, let's say, chain A, right? And open it on both sides. So we open here, that's 2 cents. And we open here, that's 2 cents, right? Now if you link one and then link 2 and link 3 using these 2 open Do we need to open all three of them? That's an interesting question. You have to think about it. So instead of doing it one step at a time, open, close, open, close, open, close, you open one chain completely. Maybe it's three, right? It will give us 6 cents. And then we have to add the closing, which will be 3, 3, and 3, giving us 15 cents. So here the solution is to think of not doing it one step at a time, sort of in a stepwise fashion, but using one chain as the holder, because opening is cheaper than closing. All right, again, very few people can solve this problem under time pressure. Given some time, you can think about it, again, walk away from the problem for a while, and then come back, and then significantly more people solve this.
I'm so confused right now.
Okay, Leroy, so the thing to do would be to actually recreate that using paper. So imagine, I'm not going to do that, but imagine you have, you can, maybe one of your relatives could do that, like cut up the, so I'm just going to do a couple. So imagine that this is one link, right, that is connected. And you can create a little chain like this using just paper. And then try to connect 4 of them. If you cut it, you're going to pay 2 cents. If you close it, you're going to pay 3 cents. See if you can create this necklace by going step by step. So opening one of the links in chain A, linking it with B, and closing it, right? That's going to be 5 cents. You see what I mean? And you will continue doing that. But remember, you need to connect D with A as well. So that's where the 3 more cents will come. So try to do it with the actual paper, and that should help you understand why the solution of using one chain by opening all the links will be a cheaper solution than going open, close, open, close, open, close. You see what I mean? You just have to try it. Then you'll see why the first solution doesn't work and the second one does. All right, let's move on to the last thing that I want to talk about today. And that is sort of these approaches to problem solving when we have more than one problem, whether it can help or slow us down. So I'm not going to talk about the other ones, the discovery, which is often used in teaching children or even adults in college, sort of a discovery approach. I'm going to dump a bunch of problems on you and you have to discover the theory or the principles. A lot of that is used in physics and chemistry and biology. We can also think of an instructional approach where we show children, learners in general, how to solve a problem and then give them a bunch of practice problems. So in discovery, they have to discover the principle themselves by wading through several problems. In instructional approach, an instructor shows one solution of one problem and then gives learners a set of problems to try. So presumably they will be using what they've learned from the teacher, how to do that. But the most interesting one is, and this is the one where I see a lot of problems with our students, is not being able to use an analogy. So this is how it goes. This is a well-known problem from Glick and Holyoke's research of the 1980s, where you are trying to solve a problem and it's not working and it's not working. Then they give you another one, which is very, very similar to the first one, giving you sort of a chance to compare the two. And if you solve the second one, turns out you can solve the first one. And this is how it works. So this is the famous tumor problem. Suppose you're a doctor faced with a patient who has a malignant tumor in his stomach. It is impossible to operate on the patient, but unless the tumor is destroyed, the patient will die. There is a kind of ray that may be used to destroy the tumor. If the rays reach the tumor all at once and with sufficiently high intensity, the tumor will be destroyed, but the surrounding tissue may be damaged as well. At low intensities, the rays are harmless to healthy tissue, but they will not affect the tumor either. What type of procedure might be used to destroy the tumor with the rays and at the same time avoid destroying the healthy issue? So when this problem is presented to participants, again, about 10% of them solve it. The solution would be continue using my paper. I'm not asking you to solve it because we don't really have time to do that. So imagine that we have a stomach and we have a tumor. So this is my representation of that. So if we have a very strong ray, I'm going to represent it as a thick arrow. What's going to happen? The tumor will be destroyed, but also all the tissue on the way will be destroyed as well, which is not a good thing. So the solution is to use multiple rays, but thinner ones, with less intensity from multiple directions. All right, like this. That would allow all of them to zoom in on the tumor and create the right intensity without damaging the healthy tissue. Good. So 90% of people cannot solve this problem in the 15 minutes that they're usually given. So how do you help them? And the idea is that if you give people another problem, that has exactly the same solution, but oops, I have a touch screen, so that's why it went to it. Even though it's the same problem, they may still have problems with that. But when they combine the two in their mind, they compare the two, it helps them to solve the first one. So here's the second one. This is called the fortress problem. You should recognize the components. A general wishes to capture a fortress located in the center of a country. There are many roads radiating outward from the fortress. All have been mined so that while small groups of men can pass over the road safely, a large force will detonate the mines. A full-scale direct attack is therefore impossible. The general solution is to divide his army into small groups, send each group to the head of the different road, and have the groups converge simultaneously on the fortress. So now, when you're solving, the solution is given to you, right? What you have to do to solve the first one, you have to equate the components of the problem from this one, the fortress problem, to the tumor problem. So you'll have to say, okay, the fortress is like the tumor. The force is like a ray. If there are a lot of people, it's a high intensity ray. If there are fewer people, it's a low intensity. And the roads are like these rays that are converging on the tumor, like the roads converge on the fortress. And this is achieved by analogy. Like I said before, only about 10% of participants given 15 minutes can solve the tumor problem. However, if they saw the fortress problem first, if those of them who are able to sort of say that the structure of the fortress problem is just like the structure of the tumor problem, then the success rate goes up 3 times. So in the final minute, we'll have to say that unfortunately, using analogous thinking is extremely difficult, even for adults, for children especially. So to help instructional endeavors, we should be more explicit in showing students how the components of one problem can be extrapolated to the components of another, making the two problem analogous. So natural application of um, analogies is not easy. It has to be taught. That's why when people who look at the discovery approach to teaching science versus people who look at the instructional approach to teaching science, the second group wins because individual discovery is very, very difficult. And that's also what's applicable to our current situation when you guys have to study at home by yourselves without being sort of directed through analogy in the classroom instruction. Well, thank you, Leroy. It was good to see you and talk to you. Thank you, Amar, for showing up. And I'll see you guys in the week. Have a good Thanksgiving.
Happy Thanksgiving.
Take care.
Have a nice day.